Good day, viewers. Welcome to the Physics Mind. Today we have a question from Thermal Conductivity, and it's a WAEC question 2021. And let's dive into the question. Okay, so the question here we have. Now, there is a diagram given, and we are told that the diagram above illustrates a composite bar of iron and copper. The bar is insulated along its side, and it has a diameter of 10 millimeter. The length and thermal conductivity of the iron are 0.15 meters and 40 watt per meter per Kelvin, respectively. And those of copper are 0.05 meters and 360 watt per meter per Kelvin, respectively. Now, if the free ends of the iron and copper are kept at 100 degrees Celsius and 0 degrees Celsius, respectively, calculate 1, the temperature theta at the interface between the bars, and secondly, the rate of heat flow along the bar. Okay, so this is the diagram. Now we are told that it's a composite bar, that it's comprising of two different metals, an iron and a copper. Now, this end of the iron is kept at a temperature of 100 degrees Celsius, and the other end of the copper is kept at a temperature of 0 degrees Celsius. And this is the interface or the boundary between the two metals. And of course, we know that this is at a higher temperature than this. So it's expected that heat is going to be transferred from this end of the iron, and then flow through the copper. But it's going to reach a time whereby the two metals will be at a thermal equilibrium, meaning that the quantity of heat that is in this iron bar is going to be the same as the quantity of heat that will be in the iron bar. So at that point, we say that the two bodies have attained a thermal equilibrium. But then at the interface, now it is expected that the quantity of heat that will be in the iron will be the quantity of heat that will be in the copper material. Okay, so let's dive into the example. All right, solution. Okay, so we know that the quantity of heat in the material, Q over T, is equals Ka into T1 minus T2 over L. All right, so let's write this equation in terms of the iron, and also in terms of the copper material, since the composite bar is made of of two different metals. Okay, so if that is so, now for the iron, now since we said that at the interface, because the question said we should find the temperature theta at the interface, and we said that at this interface, the quantity of heat for the iron is going to be the same as the quantity of heat for the copper, because the temperature at this interface here is theta. So it means that, and they are joined together, it means that at this point theta, the quantity of heat for this is the same as the quantity of heat for that. So by this, when we cross multiply, it means that our Q is going to give us KAT into T1 minus T2 over L. Okay, permit me to divide the dots in this way. All right, so for the iron, so I will denote it for Qi. So Qi represents the quantity of heat for the iron, and that is going to give us KAT, but in terms of the iron. And K here stands for the thermal conductivity of the iron. And we are told that the length and thermal conductivity of the iron are 0.15 and 40 watts per meter per Kelvin. It means that the thermal conductivity of iron is this, which is this 40. So I will substitute it, 40 multiplied by the area of the iron. We don't know the area, so it remains A. And the time taken for the heat to flow We are not given the time taken, so it remains T. So I can write it as 40 AT. Now into T1 minus T2. So T1 is the initial temperature of the ion. So at the initial temperature, the first ion of the ion is kept at the temperature of 100 degrees Celsius. So that makes it to be 100. Now minus T2, which is what? The temperature at this interface. So in this case, let's call that temperature T2 to be what? Theta, instead of writing T2, because that is the final temperature at this interface. So I will just call it theta. Then divided by the length of the ion. And we are told that the length of the ion is 0.15. So let me call this equation 1. Okay, so let's still write this equation for the quantity of heat for that of the what? The copper. So for the copper, so I will call it QC. And the same thing, the thermal conductivity of copper, which we know is equals, we are told that, and those of copper are 0.05 meters and 360 watt per meter per Kelvin. So it means those of copper becomes, the thermal conductivity is 360 multiplied by the area and time. And similarly, we are not given the area and time. So it still remains AT multiplied by, now the initial temperature of the copper. That is the temperature at this interface. That is the T1 for the what? The copper. And the temperature at the interface is what? Is T1, which we are not giving, and it's the same thing as our what? Theta. So that becomes theta minus, now the final temperature of the copper, which is what? 0 degrees Celsius. So minus 0 divided by the length of the copper, which we are told is what? 0.05. So let me call this equation 2. All right, so if that is so, we said that at the interface, the quantity of heat for the ion is the same as the quantity of heat for that of the copper. So if that is so, it means that this quantity of heat must be equal to this quantity of heat. So we can say, however, at the interface, Qi is equal to Qc. That means the quantity of heat for the ion is equal to the quantity of heat of the copper. Okay, so when we substitute, we are going to be having the quantity of heat for the ion, which is 40 AT into 100 minus theta over 0.15 should be equal to quantity of heat for the copper, which is 360 AT into theta minus 0 is theta over 0.05. So by this equation, we are going to cross multiply in order to find theta, because the question says we should find the temperature theta at the interface. So now the area AT goes with 80, so we are going to be left with 40 into 100 minus theta divided by 0.15, and to be equal to 360 into theta over 0.05. Okay, so if that is the case, so when we cross multiply, we are going to be having, or we open the bracket first. Opening the bracket, we have 40 times 100, which is 4,000, minus 40 times theta, that gives us 40 theta divided by 0.15. Okay, so 360 times theta, that gives us 360 theta, then divide 0.05. All right, so at this point, we'll cross multiply in order to find the value of theta. So cross multiplying, we are going to be having 4,000 minus 40 theta multiplying 0.05 and is going to be equal to 360 theta times 0.15. So it's equals 360 theta times 0.15. Okay, so opening this bracket, I have 4,000 times 0.05. 4,000 times 0.05, which is equals 200. So I have 200 minus 40 theta times 0.05, which is 40 times 0.05, which is equals to 2. So it becomes 2 theta and is equals to 360 times 0.15. 360 times 0.15. I have 54. So that becomes 54 theta. All right, so I'm looking for theta. What do? I'll collect lactants, and collecting lactants, I'll move minus theta to the other side. So that gives me 200 is equals to 54 theta plus 2 theta. So 200 becomes 54 theta plus 2 theta. That is 56 theta. So I'm looking for theta. I'll divide both sides by 56. So this goes with this. So theta now becomes 200 divided by 56. So I'll use my calculator to obtain that. 200 divided 56, which is 3.57. 3.57 degrees Celsius. All right, so this gives us the temperature theta at the interface between the two metals, which is between the iron and the copper. So that means the temperature at this interface or this boundary between the two of them is 3.57 degrees Celsius. So that is the first part of the question. Now the second part of the question says we should calculate the rate of heat flow along the bar. The rate of heat flow along the bar. So secondly, we are looking for rate of heat flow along the bar. All right, so we're looking for rates. And remember from my equation that Q over T is equals Ka into T1 minus T2 over L. So the rate in this case denotes what? Q over T. And K here stands for the what? The thermal conductivity of the bar, which is a composite bar. A here stands for the area of the composite bar. And then T1 minus T2 stands for the temperature difference. And then L stands for the length of the what? The bar. All right, but in this case, we are given the thermal conductivity of the iron and also thermal conductivity of the copper. So we are at liberty to what? To substitute in either that of the iron or that of the copper. We are still going to find the rates, because the rates at which the heat energy is going to be transferred is going to be the same. All right, so we already know the thermal conductivity of iron. Let's say we want to substitute into that of iron. We know the thermal conductivity of iron, but we don't know the area of the iron. We know the temperature difference and we know the length of the iron. So the only thing we need to find here is the what? The area of the iron, because we are not given the area or the area of the what? The composite bar. But then we are told that the diameter of the bar is 10 millimeter. The diameter of the bar is 10 millimeter. So it means we need to find the what? The area. And remember that the area of a cycle is given to be pi r squared. And we are not given the radius, but we're given the diameter. But remember that the radius is half of the diameter. So let's obtain the area before we substitute in our equation. So our area will now become pi, which is 3.142 or 22 over 7. It's still the same thing. Now multiplied by the radius, which is half of the diameter, and the diameter we are given is 10 millimeter. And 10 millimeter, that is 10 times 10 power minus 3. Then divided by what? By 2 all squared. Because we are looking for the what? the radius, and the radius is half of the diameter. The diameter alone is 10 times 10 power minus 3 because it's 10 millimeters. So 1 milli is 10 power minus 3. And since it's radius, it becomes half. That is why we divide it by 2. And we have what? Square. All right, so our area will now become everything here. So let's evaluate it. We have 3.142 times everything in this bracket. Okay, I have 10 exponential minus 3, which is equal to 0.01 divided by 2, all squared. Okay, that gives us open brackets 0.01 divided by 2, close bracket, squared. So which is 2.5 times 10 power minus 5. So our area now becomes 3.142 times everything here. We have 2.5 times 10 power minus 5. So our area now becomes 3.142, which is 7.855 times 10 power minus 5 meters squared. So this gives us the area of the composite bar. So we can go ahead and substitute in the equation in order to find the rate of heat flow. So let's use that of for the iron. So let's say for the iron, we have Q over T now becomes K, which is the thermal conductivity of the iron, and we are told is 40. So we have 40 multiplied by the area, which we have calculated to be 7.855 times 10 power minus 5 now into the temperature difference, which is T1 minus T2. And the initial temperature here is 100. So we'll have 100 minus the final temperature, which is the temperature at the interface, theta, and we've calculated it to be 3.57. Now divided by the length of the iron, and we are told that the length of the iron is 0.15. So divide 0.15. So our Q over T now becomes everything. So we have 40, or let's evaluate this first. So that gives us 40 times 7.855 times 10 power minus 5 times 100 minus 3.57. So we have 96.43 divided by 0.15. So Q over T becomes 40 times 7.855 times 10 power minus 5 times everything here. We have 96.43 divide 0.15. So which is equals to 642.87 approximately. Okay, so now let's multiply everything together to obtain the rate. So multiplying everything together to obtain the rate, we have 40 times 7.855 exponential minus 5 times 642.87. So we have 1.95. Okay, so Q over T is approximately 2.0 joules per second. So this gives us the rate of heat transfer throughout the iron bar. All right, thanks for watching. Please make sure you like and subscribe to my channel for more videos like this. If you have any question on places you don't understand, let me have them in the comment section and I will reply to you. Bye.